So just to kind of recap where we were at last time, went over a bit of OOP, OOD, OOA is the acronym lecture, and we kind of ended with interfaces. I got a little bit caught up with some of your homework last night. I still have some group work to grade, so that will be coming very shortly. Overall, everybody did pretty good as long as you turned it in. I was fairly happy, so good job to all of you. The only reason I was kind of behind, I was working on a grant application where hopefully I could hire an undergrad to do some fun and interesting work at some point. So we'll see how that goes. But that put me behind with everything else. But I'm sure you don't care about that. That is my other stuff I've got going on. So let's talk interfaces. We'll do a little example here as well in a bit. And actually, I just realized I don't have it open anymore because my computer restarted itself. And that's fun when that happens. Interface, please. There we go. I'll play with you later. What else? Yeah, that's about it. So we're going to get through this, and then we'll talk about decomposition. It will be lots of fun and exciting. And this is where we ended last time, right? So we're basically talking about programming to an interface, and that's one of the ways that we can enable reuse. And we started talking about this particular view here, right? So oops, I needed that anyway, but I need my pointer. So this is programming to an interface, is probably a bit of a refresher here. So we don't care necessarily what the classes are under the hood, right? We're talking to the interface. In this example here, I remember we talked about this last time, but whatever object we want to move around the screen, it's not going to matter. The subclasses that are basically interfacing here will handle that particular movement. And in this particular example, it's a little bit, might be a little bit different than some of the other interfaces you see, where here you have a generic thing that moves, and then you have other objects that basically inherit from that. So we have a little aggregation going on here. This could just as easily be split apart subclasses that are not connected to each other. They implement their own thing, and these all talk to the interface. Basically, they all interact with the interface in that way. So don't look at this and think, okay, this is exactly how you do interfaces. Basically, you have multiple ways you could implement this. This is just one example where it's kind of related more to graphics, where things are kind of point driven and pixel driven rather than, entire object driven in a way. So you could do this in different ways. But what are interfaces at a, more description, I suppose, level? These are just going to be a set of methods. So I've got that nice bold at the top there. You have an object, you have a set of methods, you have another object and a set of methods, and those are effectively the same methods, just they will be implemented differently. So with this interface notion as well, you could have more than one too, so you don't just have to have like this one interface here. Maybe I want an interface for recoloring, or maybe I want an interface for physics transformations. If I wanted to kind of slide or bump into an object or something like that, right? This is again a graphical example here where circle, square, polygon, whatever you want to represent here. So we can have different interfaces, which is nice. And really kind of the whole takeaway here is you get this notion of reuse, which is very, very handy, right? So you look at this kind of an interface, this kind of a class diagram, and you see I could very easily extend my system with this, which is why it is so handy, right? I've talked about this before, but you could add another class, right? You could add a square, you could add a polygon, you could add a ellipse, a capsule, or some kind of an ellipsoid or something. It doesn't matter as long as you're implementing the proper methods that are going to link up with your interface. It's going to be happy. And just to kind of give you an example of why this might be tricky, so here we have a circle. The circle has 1 point and a radius. All right, so that's how you draw a circle. Square has 4 corners, but you only need 2 points to represent it. You need the top left and the bottom right, or the other two depending on what you want, and then the square, they're all equidistant lines from each other, right? What if it's polygon? Polygon, you could have 2 or more points, or 3 or more points, depending on your particular needs, effectively. So then you'd have to store a list of points, how they're drawn, like in what order are they drawn in, and then you'd also implement move up, move down, move left, move right. And what does that do? It just iterates through that list of points and then shifts them. You call movable.move up, but it's really doing a lot of things under the hood. So that's kind of why you get this nice idea of reuse. I'm hoping that you're getting that out of here. All right, some points here. Advantages, and again, we are, if you don't remember from last time, it's only 2 days ago, obviously, but we are really separating out responsibilities here, right? Go back to the very beginning where we wanted classes to hide their internal mechanisms. We want privacy of our programming structure, of our data, whether it's derived or set. You don't need to know what attributes or methods we have under the hood. You just see this interface. Again, very similar to that notion of a facade where the client just sees the front end. Here it's a little bit more involved because you have more data hiding going on. So the client, again, the person calling and instantiating this class, has no idea what is behind the hood. They're just calling .moveup or .execute, .run. Nice thing here too, you can very easily swap out components, swap out objects. It doesn't have to always be movable point. Maybe you turn it into a voxel if you're going a 3D game. You migrate from 2D to 3D. Instead of a pixel, now it's a voxel or something of that nature. We have very flexible instantiations here too. So basically we don't, again, they don't have to be specific classes. We have the opportunity to basically swap in, swap out. The other term is pluggable, right? Basically, you have nice flexibility here. Reuse, mentioned that already. But we also loosen this notion of coupling. And coupling is something I talked about before. We're going to formally define it here momentarily. But basically, that is the software engineering metric where you have classes that are so tightly coupled that if you change one, you have to change the other one. Right? That's bad for reuse and for effort because that's extra work to do. If you have loose coupling, you change one class, you don't have to touch the other one. Or think of the MVC homework you all have going on right now. You update the model. Do you have to update the view? If so, you've broken that notion of coupling, of separating out responsibilities. Here, if we loosely couple things, we can plug in these different objects right behind the interface, and we don't have to change the interface. We don't have to change any of these other objects. They're loosely coupled. So that's that idea of pluggability that we have going on there. Disadvantage, not too many, honestly. So you have more complexity in your design. And what does that mean? Go back to this figure here. It's more complicated than if you didn't have this kind of a setup, right? And complicated is kind of a loose term in this regard because this honestly doesn't look terribly complicated. Right, you have an extra class here where it's your interface. And if this was something like a vehicle, you would have a movable vehicle, you'd have boat, you'd have car, you'd have truck, whatever kind of vehicles you want to represent. Doesn't seem complicated, but you have to implement this interface logic behind the scenes in your projects. Can be a little bit more complicated, but again, it's one of those trade-offs that we keep talking about in software engineering where you spend a little bit more time up front, save yourself a lot of time afterwards. But that initial hump to get over is sometimes tricky thinking about. All right, so let's do another one of these fun I show you Java and then program in Python examples, because that's just how I roll. So in Java, we have this nice keyword interface that you can implement. So it's, again, baked into the language. Very straightforward to code up. So this example here, we're going to use vehicles. And we're going to talk about the interface, then the implementations, and how we actually basically instantiate things. So here's my interface. Public interface, iManeuverable. So this is some kind of vehicle that can move, right? Go left, go right, forwards, backwards, go up, go down, set the speed, get the speed, right? Pretty standard vehicle operations, some kind of movable object operation, right? Other thing to note here, we have a set and a get function. We talked about this before with the principle of data hiding. You should really never directly set attributes. Have a get and a set function for them. Again, that really enables defensive programming, right? You can't directly operate on this variable. You need to go through effectively a layer of protection to get to it. So hopefully that makes sense why we do that. And if it doesn't make sense, think of a vehicle where I commanded to go 5,000 miles an hour. Is that technically feasible? Probably not. With a standard engine, or if it's a bicycle, definitely not. But if you don't protect against that, people may try it or accidentally try it. So that's our interface. Pretty simple. Now, if we want to implement it, here we have a car, we have a boat, we have a submarine, whatever your particular vehicle of choice would be, you could add here. We have a public class object, implements, iManeuverable. So that's how we work with an interface here. So we are going to effectively get access to these types of functions by implementing them. All right, pretty straightforward. No code in here yet. We've got this on this particular slide here. So then, if we're going to go ahead and use this, let's say that we are passing in a vehicle of some kind. We don't really care what type the vehicle is. And this is where things get interesting and where that notion of abstraction really takes hold. So here we have, right, our car, boat, submarine, obviously different physical objects. We would implement specific forward, reverse, left, right in here. But later on in our program, not in the interface, not in the vehicle classes, whichever one you instantiate, just in kind of your main. Let's say we want generic object to travel. So think of it as a game or a simulation or something of that nature. Loop through all my vehicles, right? I've got a list of entities that are vehicles. They're different types, but they're still vehicles. Loop through them and tell them to travel. You're going to pass in the reference to that object. Again, it's an iManeuverable, meaning we're talking to the interface, not the back end. We want to set its speed, move it forward, move it left, and then have it climb. So we're just going in order of operations, basically. So, is the car going to move in the same method as the boat? No, the car is going to trigger its engine. It's going to fire the cylinders. It's going to go through whatever type of car engine you have, whether it's a fancier, newer one or it's a more mechanical, older one. Just depends. Boat, is it a standard boat motor? Is it a rowboat? It just depends on how you implement things, right? And again, in those classes, you would have specific calls to these these functions. So hopefully that kind of makes sense. Again, we are adding a layer of indirection, but we are gaining the ability to call objects without caring what type they are. That's kind of the takeaway here, right? I don't care what type of vehicle this is. I'm just calling these methods that I know will be there, but they're implemented differently behind the interface. Makes sense so far? Questions at all? So I've got to update these slides in Blackboard because I threw this on last night because I figured some Python would be helpful as well. But Python implements interfaces in multiple ways, which is kind of interesting. Again, in Java, it's baked into the language, which is handy for you all if you're doing Java. I know some of you also don't like Java, so you've done other languages. You have to figure out how to do interfaces in those languages. But in Python, we have a couple of different ways that we can do things. So there's one notion in Python called duck typing. Anybody ever hear of that before? Duck typing is a fun little term. GVSU CIS350. All right, just so anyway, duck typing, it's a very Pythonic term. Basically, the definition is if it walks like a duck and quacks like a duck, it's probably a duck, is the cute little definition of duck typing. Basically, what you do is if you provide a class with particular operations, it doesn't care what type the class is, it's just going to treat it like the class that you think it is. So if I have a standard string object in Python, right, you can call length, you can call, you can slice it up, you can print it, right? So those are your standard operations. If I want to make a class that represents a special type of string, I need to implement the methods for how to actually print out this class, how to get the length of the class. And if I have these methods available, Python just treats it like a normal object. That's kind of the notion there. And why am I talking about it? Basically, in Python, if you define methods that are similar to how we showed in the interface, then it will treat it like an interface, if that makes sense. It's very loosely typed in Python. Things are a lot more flexible. But if you provide an interface class, and if you define subclasses that all implement the correct functions, kind of like we showed with the vehicle, drive, set speed, get speed, turn left, if they all have those functions available, you basically can treat it like a vehicle type. You don't have a lot of formal rigor behind it, basically. Now, there are other ways of doing things. There's the abstract base class method in Python, so ABC. Some of the links that I've got in the slides here will actually describe that, so especially this last one. It's a lot more formal and rigorous. The thing that I'm going to show you is actually going to rely on a third-party library called Zope, where it also tries to add a little bit more rigor to interfaces, among other things. If you install this library, it takes like 10 minutes to install for all the dependencies it adds in. But let's take a look at this here. Go away, thank you. So I've got a bunch of basically pre-baked code from this tutorial, and I've added some things in myself as well to demonstrate it. But what do we care about here? Am I showing this okay? Yeah. So I define an interface, and it inherits from a interface class from this library. So we're basically saying, use this library to structure what interfaces are, and implement some kind of an attribute, and then two methods. So method 1, method 2, they're generic. I'm just going to pass, meaning just return, don't do anything. So that's my interface class, pretty easy. Then I need a implementer class. And the implementer is basically going to be your specific subclass that implements the interface. Right? So whereas before we had, here's my interface, here's my implementers. So a car would be my implementer in this example. So here I've got my class, just generic out of the example. I also added on a CIS350 class where I still implement the methods, but they do different things. So the generic example, square whatever variable you pass in, and then return a string for the other one. In our particular class, instead of squaring x, we're going to also pass in y, and we have that capability because method 1 is going to allow 3 variables coming in. So just basically take x to the power of y and return that, and then return CIS350 is somewhat neat. So we have our 3 classes interface, implementers. We have a decorator here on top, basically just saying this class is a implementer, this class is an interface. This is a little bit more advanced Python. If you ever do Python, chances are you may have seen this like app notation. It's when you need to do fancy things, I suppose. All right, so then we instantiate our two implementer classes, and then let's just do some things with it. So I want to know, is it implemented by, is it provided by? And then I want to see the output of the method. So basically all this first little bit here is just printing out details about the object relationships. And then the last bit, let's actually see what it's doing. So let's run interface example. So this first bit here, let me scroll down a little bit. So is the interface implemented by the class? Yes. Is it provided by? No, meaning that it's just demonstrating what the relationship is. Who is the implementer? Who is the interface, basically. Here's the type. It's an interface class. Makes sense. Up. What interfaces are there? This is basically just testing here. The last bit is the interesting one, at least I think. Oh, I didn't update this. Let's fix this so that we can actually see it. CIS350. Quick live update. All right, so the last bit here. So output of method 1 is 16. 4 squared is 16. Output of method 2, return that string. CIS350 output of method 1. It's 4 to the power of 8. Return string for the second one, CIS350, somewhat neat. Cool. What did we do here other than have a bunch of extra code to make life difficult for ourselves? Right, because there's a lot of stuff going on here. Well, what if I want to add a third class? I could either, I could add a third class, add these same methods and call them as normal, and don't have to worry about interfaces, sure. But you always have to consider that these tend to be a lot more complicated than return a string or square a number, right? We are modeling a vehicle, modeling its engine, having it do stuff to consume the gas that comes into it, right? There are a lot of really good examples where this will save you a lot of time in the long run. So interfaces, kind of cool as long as you have a problem complicated enough to merit implementing this. Or it always comes back to that notion of, are you working on a team with other people? You all program to the same interface, and each of you implements your own particular subclass. You don't hurt the interface, you don't hurt the rest of the program. Life is good. Makes sense so far? I will put the code up on Blackboard after class and update the slides as well, because I didn't do that before class. So you can have those Python examples if you want them. If not, that's fine too. But let's move on to quality then. So we talked about cohesion and coupling a while back. Yeah, makes sense so far. Thank you. Feedback is always appreciated. Makes me aware that you are actually all there. All right, so quality. We talked about cohesion and coupling before, and we've kind of described how these are useful metrics for us. And if you remember, we want high cohesion and low coupling. So very loose coupled programs, very tightly cohesive classes. Now, there is a lot more detail than just how interrelated things are. We can be looking at things at the class level, which we've been really talking about, can be the method level or the function level. Basically, we can look at whatever level of abstraction we want to assess quality with these metrics. The other thing too, which is quite interesting, at least to me, is that these metrics were brought up in the 70s, right around the same time when we introduced data hiding. So programming is becoming a big deal, right? We still have very procedural languages, and we start thinking about quality. What does that mean? How can we actually measure it? Well, cohesion and coupling. Doesn't have to be object-oriented specific, but very, very useful. So I have a long list of cohesion levels here. So again, cohesion, how focused something is. And I'm going to use the term thing or something. Basically, it's whatever you're looking at. Function, class, module, whatever it is, the thing we're studying here. So how similar, how related are they? We have a long list of them, and I'm going to expand my cheat sheet so that I make sure that I talk to all of them here. So we have functional cohesion, which is effectively what we want. This is basically, let me pop this back in because this is one we're talking about. This is where everything functionally is very closely related. So everything in our module, our object, has a similar function. We have sequential cohesion. That means that things are grouped because like one follows the other, so they make sense kind of in an ordered fashion. We have communication cohesion. They share the same data, they operate on the same information. Basically, they're talking to the same objects or the same type of data. Right, we have procedural cohesion. Again, this is similar to sequential. Basically, function 1 calls function 2, calls function 3. They're grouped logically in an order. We have temporal cohesion. This is where things are processed at a particular time. So we have more of a time-based type of similarity. Things that happen at the same time are probably related, would be the idea there. Again, hopefully you're seeing that we're going in order from most desirable to least desirable. We have logical cohesion. This is where things that we think are similar should be grouped. So in this example, think of different types of input. If we have these modules that handle your user input, like keyboard, touchscreen, mouse, keyboard, stylus, what have you, we would group those modules together. Then we have coincidental cohesion. Basically, they're just kind of arbitrarily grouped together. So we just throw things together in a class hoping that they make sense. Now, the interesting thing here, logical cohesion, again, this is like different types that seem to have a similar function. The problem here and why this is not super desirable, because in my example, you might think, well, keyboard, mouse, yeah, that all makes sense. Let's keep them together. But they are all completely different types of input, right? You would not handle the keyboard in the same way that you would handle a mouse, or that you would handle a touch event, or that you would handle a gesture, right? These are all very specific things that you handle. Now, do you group them in the same big module? Sure, it's going to be an input event. But when you start looking at it a little bit closer, you're going to realize that they should be totally decoupled from each other. Maybe they all return the same data, what was clicked or what was touched or what the input was. But it can be, they're so separate in how they're carried out that it makes sense to group them differently. But you want things to functionally be the same? Hey, sounds cohesive. I like that. So why do we care about this? High cohesion means better maintainability, better chances for reuse. Again, if you have something that is more singularly focused, it's very easy to modify. And with that, you're not going to be having to modify other classes. Again, those of you that are doing very, very, very complicated projects, with multiple team members, if you make one change, let's say that you're doing a game with a big tile map, right? If you make one little change in how a sprite is rendered or how a collision is handled, does that only impact your little piece, or does that impact everybody else's code base and now they have to update all their code? That's kind of the notion of cohesion here. I know some of you are doing a calculator application. One of you changes how it reads in the calculus string from the user. Does that impact everybody else or not? If it does, it's not super cohesive, meaning that we are impacting other aspects of the code base. And over time, that can get really annoying. Once or twice, sure, it makes sense. It's a really important change. But if we keep making changes and everybody keeps having to refactor their code, it gets really, really annoying very quickly. And it's a lot more work. So, question to you all. Let's say that you have a project that you're working on. How would you improve cohesion? Right? What could you do to better focus your projects or your classes or your modules or your functions. What can you do? And while I'm waiting for your answers to come in, I started porting my stuff over to Godot because I've been looking at your term projects and thinking how neat they look. Man, Godot is cool. I will say that. I like Godot. It's neat. Whee! Oh, you know what? Nobody can see the code if I do that. Sorry. There you go. Git. So Git would actually version control. So these are interesting ideas. Um, that would help with maintainability, yes, but not necessarily cohesion. So that would help you separate out responsibilities in a way. I could see that argument. Any other guesses? All right. Let's start out, maybe let me better phrase this. So you're just throwing your project together in a rush. You want to get things done, frequent testing. That would be helpful. That would definitely make sure that things are performing as they should be. Doesn't necessarily get you cohesion though. So let's say that you are working on a project, you have a bunch of modules, and they're all non-cohesive, right? They're doing too much, is the example. So they're not focused classes. What are we thinking? Implementing an MVC pattern. Okay, so looking to design patterns can help. That's an interesting idea, though, because I know I mentioned MVC earlier in passing. What does MVC do for us? It separates responsibilities, right? So you look at MVC, you see working with your model, your data, working with the user interface, your views, having an arbitrator between them, that's your controller, your translation layer. So you have very specific responsibilities in MVC. The other pattern we could talk about is applying, something interface related, right? Which we've been talking about the whole time today. The key here is that we are focusing our modules, we're focusing our classes. And how do we do that? Well, if you implement MVC, you start splitting things apart, right? So the anti-pattern that I talked about yesterday, or yesterday, Wednesday, no, it'd be Monday now. Man, I'm getting old. um, you have like the God pattern or the God object, right? Where you have too many things going on. I need to turn off Hangouts, I see. You don't hear my bleeps. But you want to split things apart. Break apart these modules and subclass them out. Okay. Sorry, I need to shut this off very quickly because apparently something is super important and I'm getting a million messages and you don't need to hear Hangout bleeps. So, split things apart, focus them. Take a module that has too many things going on, rip it apart into separate classes, and then incorporate those separate classes where you need them. So your MVC pattern, you have one massive class that is rendering a view to the client. Maybe it's getting information from the user. Doing all these things, you split that apart into MVC, you're actually improving cohesion by focusing out all your different parts. Again, can be a little bit of extra effort, but you save yourself in the long run there. So good guesses. I like to start with Git because I could see the argument there. So module cohesion. I already talked about these. I must have copied and pasted the slide. Sorry about that. All right, to give you another, like a visual example here, on the left, this box, this would be a class that has low cohesion. meaning that it's doing too many things, right? So this is something relating to sending mail, whether it's an email or a letter. You have a class that handles that. Why would you have a class like this? Maybe it's an ERP system at a company, right? You're doing direct deposit or mailing people checks or something of that nature. You'd have functions to trigger that behind the scenes. Very low cohesion, not cohesive in the least because it does too much, right? If I have to make a change, there's a good chance I have to update everything in this class. Break them apart, have them do separate things. More highly cohesive. So the point is, if you see a module that's doing too much, try to break it apart. And again, we have different levels of cohesion. Functional would be your most desirable, coincidental, your least desirable. So here we have coincidental. Here we'd probably, if it were me, I'd probably say this is even going a little bit too overboard with it because I would almost group email together in a class. Maybe subclass out sending and validating, things like that, but point is break things apart. So the other side is coupling. So cohesion is focus of classes. Coupling is how interrelated they are. And what you want are classes or modules that don't have a dependency on other classes or try to minimize that. So we have different types of coupling here. We have normal coupling. So basically, it is very desirable in the fact that we only really care about maybe data coming in or going out, a little bit of control. Basically, this would be like calling a get or a set function or getting an instance of the function, something very minimal. You're not calling from class 1, class 2 dot update everything dot send email dot so on and so forth. Maybe you're calling an interface or you're calling very limited subset or something of that nature. But basically, the more that you do between classes, the higher, the tighter your coupling is. So let me show you this kind of example, and then I'll come back to it just to hopefully make a little bit more sense, I suppose. So this is one of the lovely visual representations where we don't actually show classes, we just kind of demonstrate visually what it would look like if you model out these classes and all the hooks between them. So if it's very tightly coupled, there's a lot of interdependence between them. Right, let's say that each of these circles is a class. If I update something in class A, that means I also have to update B, I also have to update C, I also have to update D. Basically, they're super tightly coupled. There is so much dependency between them that you can't break them apart. Whereas if they're loosely coupled, and again, this could be like a referencing an instance or calling a get or a set, or something very minimal where if I tweak something here, it's not really going to impact this class. If I tweak something here, it has nothing to do with this class. So the point is to try to break your modules apart. And this might seem similar to what I talked about with cohesion, but the point of cohesion was to really focus what a class does. Here we're trying to separate out as much as possible classes, really have them be kind of like atomic objects where they just operate by themselves. So, loose coupling, high cohesion, that's effectively your goal. So I've got normal coupling, common coupling, content coupling here. Normal coupling, maybe I've got some parameters coming in, some invocations to make. Common coupling, we're using the same data set, so we have some global data we're sharing possibly. Why is that a problem? If I update this global data, it's going to impact all of these other classes. So that's your common idea. And then content, that means that if I update something here, it updates something there. And again, that's a dependency where you're trying to minimize that. Hopefully makes sense. All right, so I've got a couple of questions I'll just kind of ask here, and then one is going to be the slide-do. So which one's my slide-do again? One better than the other. Okay, well, that's that one. So relationship between design patterns in OOP, OOD, OOA. Right, so if we think a little bit more broadly now, we talked about design patterns at length before, right? We're talking about these object-oriented notions here. Again, analysis is what you do at the beginning. Then you go into design, which is a little bit less abstract, more focused, and then OOP is going to be effectively your implementation. So what is the relationship between design patterns and that? That's kind of a good question because, again, design patterns, we looked at different types, right? Some of them apply better sequential. That's a good guess. You can apply design patterns at different levels of abstraction too, right? So we talked about most of our design patterns were programming related, right? We looked at the God object, we looked at the visitor pattern, right? We looked at the facade, and I gave you that big list of here's all our design patterns, whether they're behavioral, whether they're creational, right? Who cares? We have a bunch of patterns to make implementation easier. Again, think of implementation as a project-based thing. If you're just doing it for yourself for a little project, probably going to be overkill. Think big projects, lots of people, lots of effort, lots of time. We looked at the programming patterns. Those would all really be applied at the OOP layer, right? Maybe at design when we're starting to figure out our objects, our classes, things of that nature. But if you remember back when we talked about anti-patterns, we actually saw project management issues, right? We talked about the death march, where people get so focused on completing the project, even though you know it's going to fail, you still keep going. That is an anti-pattern at the project management level. So these design patterns, they can have different layers of abstraction. We can have patterns that apply at the design level. We have patterns that apply at the analysis level. We have project management patterns. All a design pattern is a known construct, basically a set of activities or objects. I'm doing this hand wavy thing, I'm realizing. Could be a class diagram, could be a project management plan, could be a Gantt chart, could be a burn up or a burn down chart, your board of user stories. You might see a pattern emerge where it fits either a design pattern or an anti-pattern. And that's either a good or a bad thing, right? So when we do all of these modeling activities, and I'm sure, I know at least in my grad class, people roll their eyes when I start talking about UML, because who does that, right? Well, at the abstract level, you can see where these patterns can be useful. They can make your life easier. They can make projects successful as long as they're applied right. But go back to that list of anti-patterns, just as a fun little aside here. Right, we have configuration management design anti-patterns. So these are things that you would apply at the config level. That's probably more at the design level, right? We have the silver bullet idea, the test-driven development idea, which I didn't realize that was considered an anti-pattern, but okay. All of these patterns can apply at different levels. So the relationship is that they will all apply. So let me leave you with this question then. So we talked about these three different levels, and again, obviously we focused more on OOP because this is all your inheritance and how you actually implement all of these ideas. But do you think one is better than the other, and why? And so again, just to kind of define this, analysis is what we do at the beginning of the project, where we start trying to structure everything. Design is where we take what we've constructed and refine it, add more objects, start designing the system as a whole. OOP is where we take that design, implement it in some kind of a language that can support everything we figured out in the design phase. So is one better than the other? Are they all necessary? Do we need analysis or not? That's kind of a question you would have to think of if you are a high-level project manager trying to assign resources to the different phases of development. Any thoughts here before I let you go for the day? Ooh, it's in blue. I don't think they're better, just different. Why is it in blue? Last one was in black. I so don't understand how Slido works, even though it's, like, so easy to use. I don't have any of these options for text size or anything like that. All right. OOD is better because it lays out the outline for the OOP stage. Okay, that's a fair answer. I don't think they're better, just different. I guess maybe let me rephrase this. Are they all necessary? Do you think we can skip a step? This is where you kind of have to think. Do I spend a month doing analysis or do I go right into design? Could I move our project timeline up by a month by skipping something? I think we had 3 answers at one point and it disappeared. If anything, you could skip OOA. I wasn't saying that you had to. I was just wondering if you could. So holy crap. What is this? Jesus. It's like you're yelling at me. Oh my god, I've got to print screen that. Yay, so I do. All right. So the real life manager in me would say they are all absolutely required. And let me say why, and then I'll let you all go. If you skip OOA, there's a very good chance you miss a critical problem domain issue. Right? Maybe you don't realize some kind of a module interaction you have, or something coming out of the environment, or. Again, these different levels of abstraction are kind of necessary to refine the project into what you want. And I would say, if you intentionally start skipping steps, you're probably going to end up with either a budget overrun or you're going to have to work overtime because you didn't properly plan things out. Now, you can try to speed things up, but I would honestly, personally not recommend skipping them if you can. Yeah, the question wasn't do you have to skip them? It's more to get you to think about what we get out of each phase in a way. So, takeaway from today, don't skip steps. It'll be worse for you in the long run. All right, I will see you all Friday, and we will start talking decomposition. So, any remaining questions at all before we end for today? Monday. Oh my god, it's Friday. Yeah, Friday the 13th. I haven't said hi, everybody. It's Friday the 13th. Yes, I'll see you all Monday. So you all have a wonderful weekend. And I'll leave you with this relaxing medley from the Super Guitar Brothers. We're awesome, by the way. Alright, bye everybody.